Alright, so this is the Specimen Paper 3. This is the first set of Specimen papers which are available on the AQA website. So let's start off with question 1, which is looking at Millikan's oil droplet experiment. So we've got a charged oil droplet, we don't know its mass, and it's falling between two horizontal metal plates, so in an electric field. So the droplet falls vertically at its terminal speed when the potential difference between the plates is 0. So we've got no electric force at the moment. A droplet of radius r falls at its terminal velocity v. Derive an expression for r in terms of v, the viscosity, the density, and the gravitational field strength or acceleration. Okay, so what we're going to use is Stokes' law. And so essentially, Stokes' law gives you the viscous force acting on a droplet. So that's this one. So that's the force, the viscous force. And if it's a terminal velocity, that will be equal to the weight force of the object. Okay, so we want an expression for r. So let's make r the subject of this equation. mg over 6 pi viscosity times the velocity. So we've got a lot of what we want already. So next, what we're going to do, well, we can replace the mass with the density times the volume. So that's what I'm going to do. So we're going to have density times by 4 over 3 pi r cubed g over 6 pi v. So we can see here we can cancel out the pi's, and we're actually going to need to rearrange now because we've now got r on both sides of the equation. So what we're going to do is cancel the r on the left with one of these, and then we're going to start moving stuff over. So now we've got r squared is equal to 6 v, and we're going to multiply that by 3 to get rid of like the 4 over 3 thing, and that's all over 4 stg, and we get this expression here. So we can do some more cancelling, and we can finally end up with an expression for r, which is the square root of 9 over this over 2 rho g. So we've got it in terms of two constants, 9 and 2, and the terms that we were looking for. So that's your radius there, and hopefully you've seen that before, so you know that that's the correct answer. Explain how the mass of the oil droplet can be calculated from its radius and other relevant data. So if we can calculate the drop's radius, we can calculate the drop's volume, and if we know the density, we can use those two things together to find the mass. So essentially, using the above method, we've got r. So mass is the density times the volume, which is the density is 4 over 3 pi r cubed. So if we've determined the radius from the method above, we can then calculate the mass there. Okay, and that's what I've just explained in the text. So let's move on to part 3. So the potential difference is now applied across the plates and is adjusted until the droplet is stationary, so the electric force is equal to the weight force. Two horizontal metal plates are 15 millimeters apart, and the mass of the droplet is 3.4 times 10 to the minus 15, which we would have calculated using the steps before. And the potential difference we can do that with is 1560. So let's first calculate the the field strength of our plates. So we're going to do that using VOZ because it's a uniform electric field. So we've got a potential difference of 1560 over a separation of 15.0. That's in millimeters though, so we need to convert that. And having done so, let's get a calculator and work out what that is. 15 times 10 to the minus 3, 60 divided by our answer, which is 1.04 times 10 to the 5 newtons per coulomb. That's your field strength. So if it's held stationary, we know that the field strength times the charge is going to be equal to the mass times the gravitational acceleration. So essentially, we can then calculate the charge using g over E. Now we've just calculated E and we've got m in the question. So let's do that. So we've got 3.4 times 10 to the minus 15 times 9.81 divided by our answer gives you a value of 3.2 times 10 to the minus 19 coulombs. So we can see that it has been ionized by charging it to by removing 2 electrons essentially from that value. A student carries out the Ball droplet experiment and obtains the following results for charges. Okay, so we've got these ones here. Discuss the extent to which the student's results support Millikan's conclusion and how the student's conclusion could be different. So, Millikan concluded that the magnitude of an individual charge was 1.6 times 10 to the minus 19. Now we can see that all of these values are multiples of that value there. So the data does support that as a conclusion, but all of those numbers are also a multiple of 3.2, which means that the student could have concluded that each charge is the smallest charge is actually 3.2, so you could get a different one. So, okay, so that's what we have got there. So the data does support Millikan, but it doesn't necessarily lead to the same conclusion as Millikan. You could also get that they're multiples of 3.2 as well. Okay, so let's move on to the next question. So we've got a filament emitting electrons which are being attracted towards a positively charged metal plate with a hole in it. Explain why an electric current through the filament wire causes the wire to emit electrons. So you should know from your circuitry that when you put a current through a wire, it will heat up, and that might mean the electrons gain enough energy to escape. Okay, so that's what we've got there. So then the next one, explain why the filament wire and the metal plates must be in an evacuated tube. Well, we need the electrons to get to the other end of whatever we're firing at, and they wouldn't if there were lots of atoms in the way. So we need to make sure the electrons don't collide with things, which is why we need a vacuum. That should be fairly intuitive there. Okay, so the next question wants us to work out the de Broglie wavelength using this potential difference. So in an electric field, if we're using it to accelerate things, the change in potential energy is equal to the change in the kinetic energy, just using conservation of energy there. So then if we want to know the velocity, that's going to be 2eV over m, all square rooted. So we've got an electron, so we know what the charge is and we know what the mass is. So the mass is 9.11 times 10 to the minus 31. 2 times 1.6 times 10 to the minus 19 times by 4800 divided by the answer square rooted gives you 4.1 blah 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 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters per second. And then using the de Broglie wavelength equation, We know Planck's constant, we know the mass of the electron, so let's multiply our velocity by 9.11 times 10 to the minus 31. We'll do 6.63 times 10 to the minus 34 divided by all of that gives you 1.77 blah 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 times 10 to the minus 11, and 2 sig figs is appropriate here, so 1.8 times 10 to the minus 11 meters. Okay, so let's finish off question 2 on the next. Okay, so the electrons we've just accelerated to high speed are fired at a metal foil, and then there's a fluorescent screen behind it, as we're seeing here. So if we're getting concentric rings, that means that's an interference pattern with our electrons, so they must have encountered something of a similar order of magnitude to their own wavelength, so they're diffracted. So it says the potential difference between the filament and the metal plate is increased. State and explain the effect this has on the diameter of the rings. So if you increase potential difference, the electrons will get faster, which means they will have a shorter wavelength. And then if they have a smaller wavelength, the amount they're diffracted will decrease, so the rings will become smaller or closer together, effectively. Okay. All right, and that's what we've got there. So that's what's going to happen if we increase the potential difference. Okay, so that finishes question 2. Let's move on to question 3. Okay, so Maxwell's theory suggests the existence of electromagnetic waves, which we can calculate the speed of. Hertz later discovers radio waves and performs experiments to investigate their properties. So this is the stationary waves experiment with radio waves. And we've got a radio transmitter and a radio detector. The wave is transmitted by a dipole aerial. The detector consists of a metal loop connected to a meter. All right, it's very straightforward. Explain how the detection of the wave by the loop demonstrates the magnetic nature of the radio waves. So, the meter is going to be measuring essentially the EMF. So if we're measuring an EMF, that means one must have been induced into the loop because it itself is not connected to anything. So if there's an EMF in the loop, that means it's been induced by a changing magnetic field through the loop. And what's created that changing magnetic field? Well, it must be the waves that we are sending towards the loop that are cutting through it. So that's what we're concluding there. Okay, so that's what we've got there. So that's how we know there's a magnetic field. Explain how the electric nature of the waves emitted by the dipole could be demonstrated. So if we're going to detect an electric field or electric nature, we need another dipole. So we've got a dipole that's emitting it, and we need another one to detect it, and it needs to be aligned with the transmitter or the dipole at the other end. So that's how we would detect it, and we would detect a changing electric field if we did that. All right, so fairly straightforward. This is just the setup which you should know about from going through the course. Okay, so let's go on to part 3. Okay, so Hertz used an arrangement like that shown in figure 4 to determine the speed of radio waves. Describe how the speed was determined, and go on to discuss how the experiments of Hertz confirmed Maxwell's prediction and the experimental evidence that suggests the light is also an electromagnetic wave. So what we're going to do is we're going to have our radio emitter, which I'm going to draw like this, and we're going to have a reflector over here, and then we're going to have something in the middle to detect the various things. So let's label our diagram. So we've got an emitter, we've got a reflector, and we've got a detector sitting right in the middle here. So that's our general setup here. So what we're going to do is we're going to set up a stationary wave between the the emitter and the reflector. So let's say, for example, we're setting up one of these, and then half a cycle later it will be in this position. So essentially what we're going to do is set up a stationary wave, and we're going to go hunting for nodes in that stationary wave. So let's start explaining what we're going to be doing. Okay, so first what we're going to do is we're going to set up a stationary wave, and we're going to create one because of the superposition of the incident wave and the reflected wave there. So that's what we're going to do first. Okay, so that's what we've got. We've got a stationary wave between the waves coming from your emitter and the ones being reflected off here. So those are going to superpose, and we're going to make a stationary wave. So next what we need to do is measure the distance between the nodes here. So for instance, we've got a node here, a node here, and a node here. So we need the spacing between adjacent nodes. So we've got that, and that spacing is going to be equal to half the wavelength. So if we've got the frequency of our radio emitter, which we can find out using an oscilloscope, and we can use frequency and wavelength to determine the speed using the equation called the wave equation. Okay, so that's if we look at the criteria, so we've described how the speed is determined. So what we need to discuss now is how these experiments confirmed Maxwell's prediction, and the evidence suggests that it's an electromagnetic wave. So first of all, we can compare this value of velocity to the one predicted by Maxwell's equation. So Maxwell predicted that we can calculate velocity by doing square root of 1 over mu0 E0. So that's how we could verify that essentially whether or not Maxwell is correct by comparing the two, and when you do, you find out that Maxwell is indeed correct. So last thing we need to do is also talk about experimental evidence that suggests light is an electromagnetic wave. So Burrows' experiment at its very basic level used a spinning wheel and a mirror. So what he was looking for is the frequency that he could spin the wheel, that the light would go through the wheel to the other side, but then couldn't come back, because essentially then it gives an idea of the speed of light from that. So that's what he was looking for in this experiment, and this experiment was kilometers in size. It's massively big because the speed of light is very big. But essentially it gave a mechanism to measure the speed of light, and he did that with an equation, and that was the speed is 4dnf, which you should be familiar with. So then it calculates the speed of light, and it comes out as 3.13 times 10 to the 8, again verifying Maxwell's prediction there. Okay, so this was his equation, and that's the general principle of how it worked. And in terms of what these principles are, d is the distance from the essentially from our light source to our mirror, n is the number of teeth he had on the wheel, and f was the frequency at which this was observed. And from this, Burrows found that the velocity was about 3.13 times 10 to the 8, which matched up with that calculated by Maxwell, verifying that it was in fact an electromagnetic wave. Okay, and that is the piece of evidence that said actually light is an electromagnetic wave, because the speed of light matched up with that predicted by Maxwell's electromagnetic wave equation. So that was finish off the answer to this question. Let's move on to question 4. Okay, so one of the two postulates of Einstein's theory of special relativity is that the speed of light in free space is invariant. Explain what is meant by this postulate. So essentially what this means is the speed of light does not depend at all on the motion of the source of light, and it also does not depend on the motion of the person observing the light. That's what that means. Okay, so that's one of the postulates. Then is asking us for the other one, and that the second postulate is that the laws of physics apply in any inertial reference frame, so they shouldn't be varied from one to another. Okay, so just some basic fact recall type questions. So then move on to 4.3. We've got two detectors that are 34 meters apart, and that's measured by an observer in a stationary reference frame. And we've got a beam of pi mesons traveling in a straight line at a speed of 95% of the speed of light, and it passes the two detectors there. Calculate the time taken in the frame of reference of the observer for a pi meson to travel between the detectors. So this should be fairly straightforward. So we're just going to use very basic motion. So in distance divided by time, sorry, velocity even. So it's at 0.95 the speed of light. So that's done like this. And when we stick that into the old calculator, so 0.95 times 3 times 10 to the power of 8, 34 divided by that gives you 1.19 blah blah blah, so 1.2 times 10 to the minus 7 seconds there. That's how much it takes for the stationary observer. Okay, so pi mesons are unstable and decay with a half-life of 18 nanoseconds. It's found in experiments that approach approximately 75% of the pi mesons that pass the first detector decay before reaching the second detector. Show how this provides evidence to support the theory of special relativity. In your answer, compare the percentage expected by the laboratory observer with and without the application of special relativity. Okay, so let's first deal without the special relativity, essentially. So we found that it would take 120 nanoseconds from the previous question, which we can see is about 6 half-lives. So we're just dealing without any special relativity. So after 6 half-lives, we should now be down. Let's work out what that is. So 0.5 to the power of 6 times 100 should be down to about, gives us a value of 0.015 blah blah blah. So essentially we've got about 1.6% of the original would be remaining at this point. But according to the measurements, we should have 25%, so something's wrong there. Okay, so that's dealing with it without the concept of special relativity. Now let's deal with it with special relativity. So let's calculate what the half-life of one of these is from the perspective of the muon. So we're going to do it like this. And when we do that, that comes out as 58 nanoseconds there. So if we look, we found a time of 120 nanoseconds to make it to the other end. So that's, you can see that's around. So then the time to go between the two places is 2 half-lives. With this theory, and 2 half-lives is essentially going to be a quarter, so you're left with 25% of your sample, or you've lost 75%. So looking at it from a special relativity perspective, we can see actually that predicts accurately what we get at the end, but without it we get something completely different. So we can see that this works there. And anytime we can experimentally verify a prediction, that's a good indication the model you're using to make that prediction is correct there. So that's great. So that completes this specimen paper 3. I hope you find that useful to review it if you've had a go at it. If you have any questions, please do feel free to comment and ask me. I'd be happy to answer those for you. But thank you very much for taking the time to watch.